Welcome back. Last time we talked about 3 out of 4 of these dimensions in describing how we designed this course in data science. And so in this segment, I want to talk about this last dimension of what I call structs versus stats. And so this is the relative importance of data manipulation versus deeper mathematics. And you can see that I've sort of put the dial here a little bit to the left. And I'll try to motivate that in the next few minutes. All right. So we already saw one example of this in the first segment where I gave some examples of data science from recent history. And one of these was Nate Silver's prediction of the Electoral College votes for the 2012 U.S. presidential election. And if you recall, this prediction was accomplished by essentially taking the average of the state polls for each state. Okay, so it didn't really require a sophisticated statistical model, and yet it had massive impact. Okay, so a quote that I think sums this up a little bit comes from Aaron Kimball at a company called Weeby Data, where he says 80% of analytics is really just sums and averages. And so if you can get these, what he means by this is if you can get these sums and averages right, if you can do it at any scale on any data that you might see, then you can always sort of build up more and more advanced techniques. Everything sort of boils down to just sums and averages. Okay, so I think this is a motivation for why focusing on data manipulation, which typically is associated with being able to express sums and averages. For example, what you can do in a database query, which we'll talk about in the next couple of lectures. That gets you a pretty long way, right? It gets you 80% of the problem. So another way of looking at this is that there's 3 main tasks involved with a data science project. There's preparing to run the model, running the actual statistical model, and then interpreting the results and communicating it. I got the animation out of order here, so you can ignore that red. But the point here is, again, Aaron Kimball, from a conversation with him is where I got this, was 80% of the work is really in this first step, where you're gathering data and cleaning it and integrating it and restructuring it, transforming it, loading it, and so on, right? So verifying all these verbs you see here, this is the hard part, right? And so actually running the model, or even choosing the model and then running it, doesn't tend to keep people up at night in practice. Okay. So, and then the joke here is perhaps that the other 80% of the work, implying that there's sort of 160% of a normal task is in data science, is in this interpreting the results. So this is the visualization and the communication and the explanation of the results. Okay. So this is another reason why I want to focus in this course on data manipulation tasks that are associated with this first number 1 task. Okay. Here, another way of looking at this is a quote that's now really old, right? So this is 12 years old or so at the time of this recording, from Doug Laney. And this is the document that first coined this notion of big data being the 3 V's of volume, velocity, and variety. And we'll talk about that in a couple of segments. But he has this quote, no greater barrier to effective data management will exist than the variety of incompatible data formats, non-aligned data structures, and inconsistent data semantics. So this, what the database community, my community, calls the data integration problem. This is the hard part. And so he was saying this back in 2001, and I would argue that it's still true today. This is the greatest barrier. And in the context of this, he was talking about this notion of variety being harder than volume or velocity. And I'll explain more about what those V's mean in a couple of segments. All right, so another vignette here is something that we like to ask the scientists we work with. So these are, astronomers and oceanographers and biologists. We ask them sort of informally how much time they spend, quote, handling data as opposed to, quote, doing science. Now, we let them interpret these quotes however they want, but what we mean by doing science, choosing a statistical method or designing a statistical model, they absolutely consider part of their science. And so what we mean by handling data is all the other crap, the format conversions and so on. And so what do you think the most common answer is here? Well, you can guess to yourself for a second, but they don't even blink. They say things like 90%. And so this number should, give pause, right? This is taxpayer money that goes to federal funding agencies to come back to pay some postdoctoral fellow to spend 90% of her time doing something that she doesn't even consider science. And so this is why I think it's really important as a data scientist to focus on this problem. Now, you might say, well, that's just science. What about business? But as I will try to make the point throughout the course, there's a increasing alignment between what's going on in business and what's going on in science. Okay, and we'll talk about that more in a couple of segments. All right, so if 90% of the problem is handling data, boy, we ought to spend a lot of attention on that. All right. So, another argument that sort of follows on the first slide that I gave is that structs, the data manipulation platforms and databases in particular actually go a pretty long way to being able to express more advanced things. And this isn't just a matter of, oh, well, you can express anything if you have sums and averages. It's also even fairly advanced techniques. There's an increasing amount of interest in figuring out how to get this stuff into the database. Okay. And so this is a slide I've taken from Christian Grant, where he argues that, look, if you consider databases versus statistical packages such as SAS or MATLAB or R or SPSS, this is what they're doing now. They're downloading data to use in their favorite statistical package, frequently under the assumption that, well, of course I have to, right? Of course that's the only thing that could possibly express this. Well, look, most of these stat packages, the first thing that you'll do is read the data off of disk and load it into memory, and then start calling functions on it. Well, increasingly data sets simply don't fit in memory on a single machine, certainly not on your laptop. And so you have a couple of choices here. Either you shift into some kind of fancy cluster version of the tools for which they exist for things like SPSS and MATLAB, although they're quite expensive, or you sample the data so that you only can work with a subset that actually does fit in memory. And you'll see this to be very, very common, is that it's just par for the course to take a sample of the data in order to be able to work with it efficiently, right? But the point here is that this isn't really required if you use different packages. If you, in this case, the argument here is that if you can use databases, if you can figure out how to perform your task in the database, you'll get the scalability for free. Moreover, these toolkits don't necessarily have any kind of notion of parallelism, right? So even if it does fit in memory, every machine you buy nowadays has, at least 4 cores in it, and probably more like 8, and soon to be, 12 and 16. So to take advantage of all those cores on your problem is something you're going to be looking for in a package. And this is something that databases can do automatically. Most databases, not all. In fact, the ones you may be familiar with, MySQL and Postgres, typically do not, but other databases will, and we'll talk more about this. Okay, so you get parallelism for free if you can use a database, and you get scalability beyond the size of main memory for free if you can use a database, and that's perhaps a big if, and we'll talk about it. Okay, so let me give you an example here, and you'll actually do this as part of a homework assignment, but can you express matrix multiplication in SQL? And if you can, then I'd argue, well, hey, now any formula that you can express using matrix multiplication, you can perhaps express in SQL by doing this over and over again. Okay, and the answer is yes. And in fact, the simplest version of this is pretty straightforward. So if you haven't ever seen SQL before, don't worry, we'll talk a little bit more about this. But if you have, bear with me. Imagine you have 2 matrices A and B. Oops, I'm using the wrong device here. 2 matrices A and B. And what you want to do is find all the, the representation of each matrix here is as a row ID, column ID, and value. Right, so that's your relation. Now, this is a very inefficient relation if your matrix is dense. And I'll let you think about why, well, I'll tell you why, and you can think about it a little bit more as well, is that, an implicit representation of this only has let's say you have let's say you have 5 rows and 6 columns, then you only need the 30 values, 5 times 6. But here you have to do 30 row IDs plus 30 column IDs plus 30 values. So you sort of tripled the size of your data relative to, efficient main memory representations. So why would you do that? Well, it turns out that a lot of matrices in practice are sparse, and I put that word right up here at the top. In a sparse matrix, not all the cells actually have a value, and so you don't actually need to store them. And so this representation, in terms of explicitly having a row ID, a column ID, and a value, turns out to be pretty efficient. Okay. And in fact, sparse matrix solvers, this is exactly the kind of representation they use internally. All right, so if you have a sparse matrix, and if you encode it if you represent it in a database, then expressing matrix multiply is not too bad. What you want to do is find all the columns, for each column number in the matrix A, find the corresponding row number in column B, and then add up all the contributions to the new value. And I'll show a diagram of this after. In fact, you know what? Let me skip going into too much detail about this right now, because I'm going to talk about this in detail in preparation for the homework where you'll do this. So right now, I guess the takeaway, what I want you to take away is that representing matrices inside of a database sounds very unusual. It's actually not the world's worst idea. And in part of the readings from this Mad Skills paper, you'll see why. So right now, I just want you to take away that it can be done, and it's not necessarily a terrible idea.